Okay, here's another approach, something we can do sometimes if we spot certain things. This one, um, we, we kind of make a note um, that this is, well, it almost looks like a geometric series. Fact is, you could, if you wanted to, I talked about this in one of my last examples. If you really wanted to, you could do this. Both of these are series which you could then expand. Um, this is the negative of this series. Well, we negative 1 to the n with an x to the n. And this series is times n equals 0, another negative 1, x to the n. Now you'd have to expand these before you multiply. So that's where the work comes in. So maybe you're not into that. Maybe you don't really want to try that. But so let's make a note here. Let's say this looks, we know a little bit about differentiation and integration, but this looks, if you make a note, what if g of x were equal to x plus 1 to negative 1? What if? So there's a big what if. Then g prime of x would be negative x plus 1 to negative 2, which you notice is exactly what f of x is up here. In other words, this is the function we need to expand. So all we have to do is take this function, expand it, and then differentiate it. Okay, so in other words, I can start with this, start with g of x equal to this. And we saw already that this was this here, which comes out this way. Basically, it's the alternating geometric series with that plus x in there. So then g prime of x, which we already know is our function, right? We already know that's the minus 1 over x plus 1 squared. We know that that will just be the derivative of all of this. So now you start differentiating this thing. So you'd have n equals 1, and notice 0 is not going to make sense because when you bring down that n, well, let's see, I guess I don't really need that. Where is okay, I have n and I have x to the n minus 1. Okay, so this is my series now. And of course, when we started with this form here, we started with this, we knew that we, of course, had this. Differentiating that is not going to bring in those endpoints. And we already saw how that worked. We could check it if we wanted to, but it isn't going to bring them in. So we'd be satisfied with this. We've done that enough times to see that that won't work, but you could do a quick check if you really want those endpoints. Notice if x is 1, you're just going to have this negative 1 to the n times an n, obviously divergent. If x is negative 1, you'll have some form here, maybe all negatives, maybe alternating. Doesn't matter because there's an n in there and it will not converge. It'll diverge by the nth term test. So you're not going to add in those endpoints, negative 1 and 1. This is your answer. It's finished.